All right, so what happens when p equals 1, which is the special case here? Okay, then sum from n equals 1 to infinity of 1 over n to the p will be sum from n equals 1 to infinity of 1 over n to the first power, which is sum from n equals 1 to infinity of 1 over n. Now this sum turns out to show up in a lot of places and be really important and be a special case in a lot of situations. And it has a special name. It is called the harmonic series. The harmonic series. I think that actually does come from music. I think the series 1 over n gives you something like the overtones of a string or pipe with a specific length. Then the harmonic series gives you the overtone frequencies, something like that. I'm not sure exactly. You can look it up. It's fun. All right, but does it converge or not? That's all we care about. Does it converge? All right, so again, we can define f of x equals 1 over x. That is positive, continuous, and decreasing on 1 to infinity. So we can use integral test. You can just go ahead and do that if you want. It's not hard to do. The integral test. So we're just going to do integral from 1 to infinity. So the integral test always goes 1 to infinity because that's basically what n does, of 1 over x dx. And so that is ln of absolute value of x from 1 to infinity. I wrote it this way, which some people will do. What it means is the limit as b approaches infinity of ln of, and we can drop the absolute value because from 1 to infinity everything's positive, so it's just ln x from 1 to b. So usually I put that limit statement before I do the antiderivative, but you can do the antiderivative and then do the limit statement too. That's fine. All right, so this is limit as b approaches infinity of ln of b minus ln of 1, which is 0. All right, but ln is an increasing function, so as b approaches infinity, this limit approaches infinity, so this integral diverges. Integral from 1 to infinity of 1 over x dx diverges. So the sum from n equals 1 to infinity of 1 over n diverges. We get to make what is a fairly poetic statement in mathematics, which is that the harmonic series diverges. So we'll come back to this statement again and again. So the harmonic series diverges. That is a special case of the statement. The p series converges for, and now we know p, only p less than 1, greater than 1. I always mix that up. Converges for p greater than 1 and diverges for p less than or equal to 1. And then conveniently, the cases that we threw out at the beginning where p is negative are also less than 1. So there you go. So the p series, sum from n equals 1 to infinity of 1 over n to the p. So we're going to keep coming back to this p series. P series. Sum n equals 1 to infinity of 1 over n to the p. All right. Whether it converges or diverges depends on the value of p. Converges for p is greater than 1, diverges for p less than or equal to 1. If n equals 1, we also call it the harmonic series, but it still diverges. There you go. That's all I got to say about that. Now, and your homework doesn't really call for you to say anything about p series, but when we get to the comparison test, knowing that a p series converges for p greater than 1, and diverges for p less than or equal to 1 is going to be extremely important and useful. All right, so hold on to this for later use. All right, now you are going to have a certain homework, which I apparently lost. I'm going to do that homework. Oh, here it is. Okay, so your homework assignment, it's posted, so you can stop the video now if you want to just go look it up. Go do the homework. It is, so I'm going to be saying things like SK for Stuart Kokoska. That's our new book that is posted on the web. Section 9.3, page 683. Is it really page 683? Yes, it is. Number 11 through 23 odd. and 31, 33, 35. Look at the examples I did number 20 and 22 earlier, because that's basically all that these are. It's just using integral test, okay? All right, there you go. That's integral test. Woo!